There is a dangerous trap in the world of quantum computing. It is a trap that 90% of people fall into. It is a trap that makes you feel smart but keeps you useless. It is called the pop science plateau. You know what I am talking about. You have watched the videos. You know about Schrödinger's cat. You know about entanglement. You know that a qubit can be a 0 and a 1 at the same time. You have heard the analogies about the coins spinning and the balls going through walls. You feel like you get it. But then you open a real scientific paper, or you look at a line of real quantum code, or you look at a job application for a quantum engineer at Google or Qiskit. And suddenly, you are hitting a brick wall. You see symbols you don't recognize. You see words like Hamiltonian, eigenstate, Hilbert space, and Hermitian conjugate. And you realize with a sinking feeling in your stomach that you don't actually know quantum computing. You just know the trivia. You are a tourist standing outside the castle, admiring the walls, while the wizards inside are actually casting the spells. Most people stop here. They say, "Oh well, I guess I need a PhD in physics to go any further." They give up. They go back to watching sci-fi movies. But you are not most people. You are here because you want to enter the castle. You want to move from being a spectator to being a player. You want to understand the machinery of the universe well enough to build things with it. Today, we are going to break you out of the pop science purgatory. We are going to lay out the roadmap to advanced knowledge. We are going to strip away the scary terminology and show you the actual engines that run this technology. We are going to talk about the math, the algorithms, and the hardware in a way that doesn't treat you like a child, but doesn't require you to be Einstein either. If you are ready to stop talking about the magic and start learning the mechanics, please hit that subscribe button right now, because the gap between the amateur and the expert is smaller than you think, and we are going to cross it today. The first step in advancing your knowledge is a mindset shift. You have to stop thinking about physics. You have to start thinking about information. When you are a beginner, you obsess over the electron. You ask, how can it be in two places? Is it a ghost? Is it a wave? The advanced student stops caring about the how and starts caring about the what. In classical computing, we don't worry about the silicon atoms in the transistor. We worry about the logic. We worry about the flow of information. In quantum computing, you need to treat the qubit not as a mystical particle, but as a vector. This brings us to the first gatekeeper, the thing that scares everyone away. Linear algebra. Do not click away, listen to me. Linear algebra is not scary, it is just a way of organizing lists of numbers. If you want to advance, you have to stop visualizing spinning coins and start visualizing arrows. Imagine a sphere, a perfect ball. This is the playground of the qubit. We call it the block sphere. A classical bit is a point at the very north pole 0 or the very south pole 1. It can only live in those two spots. A qubit is an arrow that starts at the center of the sphere and points to the surface. It can point north, it can point south, but it can also point to the equator. It can point at a 45-degree angle. Advancing your knowledge means learning how to navigate this sphere. When we apply a gates like the Hadamard gate or the Pauli-X gate, we aren't doing magic. We are just rotating the arrow. That is it. Quantum computing is just rotating arrows inside a sphere. If you want to be an expert, you need to learn how to represent that arrow as a column of numbers, a vector, and the rotation as a square of numbers, a matrix. When you multiply the square by the column, the arrow moves. That is the secret. That is the math that runs the universe. So your first homework assignment is not to read another book on physics. It is to go to Khan Academy or YouTube and spend a week on linear algebra. Learn what a matrix is. Learn what a dot product is. Once you realize that superposition is just a fancy word for pointing the arrow sideways, the fear disappears. You gain power over the system. Now let's move to the second pillar of advanced knowledge, the algorithms. In the beginner world, everyone talks about Shor's algorithm. This is the one that breaks encryption. It scares banks, it scares spies. But if you want to be taken seriously in this field, you need to stop talking about Shor's algorithm. Why? Because Shor's algorithm requires millions of perfect qubits. We don't have those yet. We might not have them for 20 years. If you walk into a job interview and talk about Shor's algorithm, you look like a dreamer. The advanced student focuses on the now. They focus on the NISQ era. NISQ stands for Noisy Intermediate Scale Quantum. It means the computers we have right now, they are small, they are noisy, they make mistakes. But we can still do amazing things with them if we are clever. To advance, you need to learn about VQE, the variational quantum eigensolver. This is the algorithm that is actually going to change the world in our lifetime. Here is how it works and why it is brilliant. Imagine a landscape of mountains and valleys. You are trying to find the lowest point in the deepest valley. This represents the ground state of a molecule. If we can find this, we can design new drugs, new batteries, and new fertilizers. A quantum computer is very good at calculating the height of the land at any specific point, but it is bad at remembering where it has been. It is bad at navigation because of the noise. A classical computer, your laptop, is great at navigation. It is great at saying, okay, we were here, let's try moving left. So VQE creates a marriage, a hybrid loop. The classical computer acts as the coach. The quantum computer acts as the runner. The coach says, try running with these parameters. The quantum runner tries it and shouts back, my energy level is 50. The coach says, okay, that's too high, adjust your stride and try again. The quantum runner tries again, now it's 40. The coach says, good, keep going in that direction. They loop back and forth thousands of times. The classical computer handles the optimization logic, and the quantum computer handles the complex wave function simulation. This is how we are going to win, not by throwing away classical computers, but by making them work together with quantum processors. If you can write code that implements a VQE loop using tools like Qiskit or Circ, you are no longer a beginner. You are an engineer. You are solving problems that are actually relevant to the industry today. Now let's go deeper. Let's talk about the thing that actually makes quantum computing hard. Interference. Pop science teaches you that quantum computers are fast because they try every possibility at once. They say a classical computer tries one password at a time. A quantum computer tries all passwords at once. This is a lie. If you try all passwords at once, you get a result that is a jumbled mess of all passwords at once. You don't know which one is right. To advance your knowledge, you have to understand amplitude amplification. This is the mechanism behind Grover's algorithm, the search algorithm. Think of a pair of noise-canceling headphones. How do they work? They listen to the noise of the airplane engine, and they create a sound wave that is the exact opposite. The peak of one wave meets the valley of the other. They cancel out. Silence. Quantum computers work the same way. When you run an algorithm, you have a lot of wrong answers and one right answer. A good quantum algorithm is designed to create destructive interference for the wrong answers. It makes the probability waves of the wrong answers cancel each other out. And it creates constructive interference for the right answer. It makes the probability wave of the right answer spike upward. So when you finally look at the qubit, nature is forced to give you the right answer. You aren't trying everything at once. You are choreographing a dance of waves so that the wrong dancers fall down and the right dancer is left standing. Understanding this, that quantum computing is the art of manipulating interference patterns, is the moment you graduate from novice to adept. It changes how you code. You stop thinking in if-then statements. You start thinking in phases and rotations. Now let's talk about the hardware. The beginner thinks a qubit is a qubit. The advanced student knows that hardware is a battlefield. There are different types of quantum computers and they are at war for dominance. If you want to be an expert, you need to know the combatants. Combatant 1: superconducting qubits. Google, IBM. These are man-made atoms printed on a circuit board. They are fast, they are powerful, but they are extremely fragile. They have to be kept at temperatures colder than deep space. They only last for microseconds before they collapse. Combatant 2: trapped ions. IonQ, Honeywell. These are actual atoms, real nature, trapped in a magnetic field and zapped with lasers. They are incredibly stable. They last a long time, but they are slow. Doing an operation on them takes time. Combatant 3: photonic qubits. PsiQuantum. These use particles of light. They can work at room temperature, no giant freezers, but light is hard to store. Light wants to fly away. Why does this matter to you? Because if you write code, you need to know what machine you are running on. If you are on a superconducting machine, you have to be fast. You have a short runway before your qubits die. You need to optimize your circuit depth. If you are on a trapped ion machine, you can run longer, more complex calculations, but you have to be careful about the connections. Advancing your knowledge means understanding the topology of the chip. In a classical computer, you can connect any bit to any bit. In a quantum computer, qubit 1 might only be able to talk to qubit 2. It can't talk to qubit 3 directly. If you want to entangle qubit 1 and qubit 3, you have to use qubit 2 as a bridge. This adds noise, this adds error. The advanced engineer knows how to map their problem onto the physical chip to minimize these swaps. They treat the hardware with respect. This brings us to the biggest challenge of all, the final boss of quantum computing. Error correction. If there is one phrase that will get you hired instantly, it is quantum error correction. Here is the problem: the universe hates quantum computers. Everything tries to break them: heat, radiation, magnetic fluctuations, even cosmic rays from space. If a butterfly flaps its wings in the wrong room, your qubit flips from a 0 to a 1, and your calculation is ruined. Classical computers have it easy. If a bit flips, we have backups. We just copy the data. But in quantum mechanics, there is a rule called the no-cloning theorem. You cannot copy a qubit. It is impossible. If you try to copy it, you have to measure it, which destroys the state. So how do we back up our data if we can't copy it? This is the genius of error correction. We smear the information out. Instead of storing one bit of information on one physical qubit, we store one bit of logical information across a web of 9 or 40 or 100 physical qubits. We entangle them all together into a logical qubit. If one of the physical qubits gets hit by a cosmic ray and flips, the others notice. They say, "Hey, Dave just flipped. He's supposed to be a 0, but he's acting like a 1. And because they are entangled, they can force him back into line without ever measuring the actual data. They heal the system without looking at it. This is the frontier. Right now, we are trying to build machines where the error correction actually works. We are trying to reach the break-even point where adding more qubits makes the system better, not worse. If you want to advance your knowledge, dive into the surface code. Dive into stabilizer codes. It is complex, yes, but it is the most important problem in science right now. Now let's talk about how to actually learn this stuff without going back to university. You need a curriculum. Step 1, the foundation. Don't start with physics, start with Python. If you don't know Python, learn it. It is the language of the quantum SDKs. Then brush up on linear algebra and complex numbers. You don't need to be a mathematician, but you need to know how to multiply matrices. Step 2, the frameworks. Choose your weapon. Qiskit IBM is the most popular. Circ Google is powerful. Penny Lane is amazing for machine learning. Go to the IBM Quantum Learning website. It is free. It is brilliant. They have a textbook that is interactive. You can run code right in the browser. Step 3, the hands-on practice. Stop reading and start coding. Build a random number generator. Build a teleportation circuit. Then try to implement VQE for a simple molecule like hydrogen. When you see the energy curve converge on your laptop, you will feel a rush of power that is indescribable. Step 4, the community. Quantum is lonely if you do it alone. Join the Qiskit Discord. Join the Quantum Open Source Foundation. Participate in a hackathon. Quantum hackathons are happening all the time. You team up with strangers, you have 24 hours to solve a problem, and you get mentorship from real engineers. This is how you build a portfolio. And that is the keyword, portfolio. If you want a job in this field, nobody cares if you watched a documentary. They care if you have a GitHub repository full of quantum circuits. They want to see that you have grappled with the noise. They want to see that you understand the constraints. Finally, I want to address the elephant in the room. Quantum machine learning, QML. This is the buzzword of the century. Everyone wants to combine AI and quantum. And yes, it is exciting. The idea that quantum computers can find patterns in high-dimensional data that classical computers miss is intoxicating. But as an advanced student, you must be a skeptic. There is a lot of hype in QML. A lot of papers claim quantum advantage when they haven't really proven it. To advance, you need to learn to read scientific papers critically. When you see a headline, "Quantum computer solves cancer," you need to dig in. Ask how many qubits did they use? Was it a simulation or real hardware? Did they compare it to the best classical algorithm? Usually, you will find that a classical computer could have done it faster. And that is okay. We are in the infancy of this technology. The goal right now isn't to beat classical computers at everything. It is to find the 1 or 2 tiny niches where quantum has a hope of winning. If you can find those niches, if you can identify the specific types of kernels where quantum spaces offer a geometrical advantage, you are ahead of 99% of the population. So why do this? Why go through the pain of learning matrices and error correction? Because we are standing on the edge of a new epoch. Think about the people who learned to code in the 1970s. They were working with punch cards. They were working with slow, massive machines. People told them it was a waste of time. But those people became the architects of the digital age. They built the internet. They built the smartphone. They became the titans of industry. Quantum computing is the 1970s all over again. We are working with punch cards, primitive circuits. We are working with massive, slow machines. But the potential is infinite. We aren't just building faster calculators. We are building machines that mimic nature itself. We are building machines that can simulate the folding of proteins to cure Alzheimer's. We are building machines that can design catalysts to pull carbon out of the atmosphere and solve climate change. We are building machines that can understand the fundamental fabric of reality. The people who learn this now, the people who push past the pop science plateau, will be the architects of the quantum age. You have a choice. You can stay in the audience watching the magic show, clapping when the rabbit comes out of the hat. Or you can step backstage, you can learn how the trick works, you can learn how to build the hat. It will be hard, it will be frustrating, you will feel stupid sometimes. But I promise you, the view from the inside of the castle is worth it. The universe is speaking a language. It is a language of vectors and phases and entanglement. For the first time in history, we are learning to speak it back. Don't you want to be part of the conversation? If this roadmap to quantum mastery lit a fire in your brain, if it made you realize that you are capable of more than just watching, please hit that like button. It helps us find more potential engineers. And share this with a friend who is stuck in the tutorial loop. Tell them, let's go build something real. Hit subscribe. We are going to keep deep diving into the code, the hardware, and the future. Let me know in the comments, what is the biggest barrier stopping you from learning quantum computing? Is it the math, the coding, or just not knowing where to start? I'll see you in the Hilbert space. Stay curious.